just left over to deliver the last lecture. So we already did quite a bit of foundations of white dwarfs and how they explode, how they ignite explosion, what the simulation techniques are, what the progenitors are, and how we actually picture the explosion itself. What I did not talk much about so far was do these explosions that we model in the end look like the observed Tapani supernovae. So this is the lecture for today. So today we will take a look into how we really assess the models, the validity, and how we can judge on our modeling assumption by really comparing the outcome of our simulations to actual observation. So this is the observables predicted from thermonuclear explosion models. So in order to understand how we really derive these observables, I will first talk a bit more about the formation of electromagnetic observables in Type 1a supernovae, what the specific processes there are that give rise to the formation of the observables. And then I will actually give you an overview of the electromagnetic observables predicted from different scenarios of thermonuclear supernova explosions. And of course, electromagnetic observables are not the only information that we get on the models. This is perhaps the most useful one because we have most of the data from optical observations of Type 1a supernovae, but there are alternatives, and I will finally also at least mention some of these alternatives. Now let's start with the main observables. So the main astronomical observables of Tapani supernovae, of course, their spectra and the light curves, and they have become available with very high precision at a rather large number of objects. So we, over the last maybe 10 or 20 years, people have taken lots of very precise data on Type 1a supernovae. In particular, they have actually set up specialized surveys that with one telescope observe supernovae every night, so that you don't have so much of an uncertainty by comparing the data of different telescopes, and you get actually spectra of nearby supernovae almost every night, so you have lots of information about them. But there are also observables in addition to the optical data taken around peak luminosity, and these can be also useful to distinguish between different scenarios for Type 1a supernovae. And I've already mentioned the gamma ray observations of supernova 2014J. That told us very fundamentally that our overall picture of Type 1a supernovae resulting from thermonuclear explosions of white dwarfs produced in nickel 56, and then the light emission being powered by the decay of nickel 56 is actually confirmed. Other constraints of models come from rates of occurrence of these objects. So we would actually then make predictions from progenitor models of how often we expect these objects then to go off as a thermonuclear supernova, and can compare this to the observed rate of Type 1a supernovae. And then, of course, our models predict specific nuclear synthesis, and this can be then compared to observations of, say, meteoritic abundances in the solar system, or observations of abundances in stars from spectral measurements. And this is actually something we can also get information on. Now, spectral and light curves. So these are formed powered by the nuclear decay in the ejecta of supernovae, and then the nuclear decays heat up the ejecta, and this produces photons, and these photons then are transported through the ejecta, and of course they interact with the ejecta material, and this gives then rise to characteristic spectral features that are predicted by the models and can be compared to observations. So the task for people who predict observables from models is to actually describe all these processes theoretically. Unfortunately, I don't have time to go into the general theory of radiation transfer or the numerical techniques, how this is achieved in the end, but I want to actually point out at least some basics of how this specifically works in Type 1a supernova ejecta, so what is particular about them. So the unstable isotopes that are produced in the explosions decay and heat the ejecta on the corresponding decay time scales. And then that leads in the end to emission in the optical range. So nuclear transmutation changes the composition of a nucleus by either emission of alpha particles, emission of electrons and electron antineutrinos at the beta-minus decay, or the emission of positrons and electron neutrinos in the beta-plus decay. The alternative is that we could also have for the nuclear transmutation from a proton to a neutron inside a nucleus, the capture of an electron from an inner atomic shell, and this actually then leads also to the emission of a neutrino. Now this shell is then left with a hole, and this has to be refilled, and the refilling of the shell is by other electrons from outer shells actually filling in this hole, and this then gives rise to the emission of X-rays, or the energy that's needed to fill that hole in the atomic shell structure is then transported to an outer electron of the atomic structure, and this is ejected, and this is then called an Auger electron. So in this way, by nuclear transmutation, a new nucleus is formed, and this is usually then formed in an excited state and has to decay to a ground state, and this happens via the emission of gamma rays and or internal conversion electrons. So this is again the transfer of energy of the excited nucleus to an outer atomic electron, which can also be ejected. Okay, so which nuclear decays are important for Tapani supernova formation of observables? Well, the most important, of course, is the decay of nickel 56 over cobalt 56 to iron 56. So here's a table that was put together by Anders Ekstrand for his handbook of supernova contribution, and this gives you actually the fractions of the different decay channels, and you see that the nickel to copper decay is in large parts via the emission of gamma rays, and only a small fraction due to electron emission, and the cobalt to iron decay also is largely due to emission of gamma rays, but you have some leptonic contributions here as well. And there are other unstable isotopes that play a role in that are produced in the observations in the thermonuclear explosions of supernovae. They are not that abundant in the end, but their importance is that they actually have, in parts, much longer decay time scales, and they also decay through other channels than gamma rays, and therefore in the late phase of the emission of a supernova, they may be the dominant energy source. Now, the decay products heat the ejecta, provided that they are still trapped in the dense ejecta material. So in the early phase, up to about 3 years after the explosion, the ejecta are still optically thick enough that they are powered mainly by the nickel decay chain through gamma emission. Later on, then the nickel-cobalt decay chain has actually extinguished at some point. The ejecta have become transparent to gamma ray radiation due to expansion, and then we have the originally small contributions from radioactive species that decay through other channels, through the leptonic channels, that they may actually become the dominant energy source, because the spectrum may be transparent to gamma rays already, but not yet to electrons. So the electrons can still deposit their energy, and even if you have a production of, say, cobalt 55 in a ratio of only 10 to the minus 4 or so, it still may substantially then contribute to the late light curve. Now, the deposition of the energy happens by interaction with the ejecta material. So X-rays have rather high energies, and therefore they make no distinction between free and bound electrons, and they interact with these electrons via Compton scattering, and this heats up the ejecta material. Electrons ionize and excite the gas, and gamma X-ray absorption is dominated by the photoelectric absorption on inner shell electrons of heavy nuclei. Now, one specific fact on type 1a supernova optical observables is that it's usually rather difficult to say where a photosphere exists in these objects. So this is the place where the spectrum originates. So this is the place in the ejecta where the optical depth is about 1. And this is something that can only be ambiguously determined in type 1a supernovae, because there is no, as opposed to stars, there is no bottom of an atmosphere where the optical depth raises, or the opacity raises steeply for all wavelengths. And also we don't have any hydrogen or helium that provides an optically thick continuum, as is the case for type 2 supernovae. So what one has instead in type 1a supernovae is what people call a pseudo continuum, and this is actually just formed from a very dense distribution of overlapping metal lines. And the density of these lines and the location depends on wavelengths. So therefore, it is impossible in type 1a supernovae to ascribe a unique photosphere. So this is wavelengths dependent. For instance, an optical depth of 1 is never reached in the infrared. However, still, approximately the concept of the photosphere applies to at least the early formation of the observables. So here, over a certain wavelength range, the metal lines are sufficiently dense to form a continuum-like structure. And therefore, people talk about the early phase of the formation of spectra, about when the ejecta are still dense, as the photospheric phase. So here, the spectrum is dominated by absorption lines. Then, of course, we have, due to the expansion of the ejecta, that the ejecta dilute and progressively become more transparent to radiation. So that means this photosphere, as much as it exists at least, recedes inwards with time. Now this is an interesting fact, because this allows for a technique called abundance tomography that I already mentioned. The photosphere recedes inwards and tests subsequently deeper layers of the ejecta. This is then where the spectrum forms. So that means if you observe the supernova and take a spectrum every night, it will come from a deeper into deeper layer, and in this way you can test the chemical layering, the chemical structure of the ejecta of supernovae. So this was work done, for instance, by Matthias Stehle at MPA in 2005. Now, very late, the photosphere, at least the pseudo-continuum, where it's produced by the pseudo-continuum, reaches the center of the ejecta, and then the ejecta become completely transparent, and then they change their character. They are then dominated by the emission lines of nuclear synthesis products in the central parts of the ejecta, and this is called the Nebula Phase. Well, this happens rather late, only 100 days or so after the explosion, or later, a few hundred days after the explosion. So then the supernovae, of course, are already rather faint. Nonetheless, it's important to take data on this Nebula phase, because this is actually the phase where really the inner part of the ejecta are tested, where the explosion took place. So this is perhaps a place where we could learn much about the actual explosion mechanism. We were on spectral lines. So in a photospheric phase, these spectral lines result from emission and absorption in a radially expanding material. And you all know that this process in principle gives rise to typical P-Cygni shapes of the ejecta. So this is seen, again, an indication that we have high velocities of the expanding material. Now, the ejecta expansion is something that is important for the formation of the observables. The explosion phase is governed by strong and complex hydrodynamic flows, as we talked about yesterday, and the release of nuclear energy in the burning is rather short. It lasts only for a second or so. The expansions of the ejecta, however, then will make the potential gravitational energy, the potential of the gravitational energy shallower as the ejecta expand and the ejecta cool. At some point, all the energy released in the nuclear burning will have been used to overcome the gravitational field and to accelerate the ejecta to their final velocities. And then the ejecta continue to expand ballistically. That means the kinetic energy of the ejecta dominates the total energy of the ejecta. The gravitational binding energy and the internal energy have become negligible. And the material is no longer accelerated, but expands in a self-similar way. So in this way, then hydrodynamical effects are frozen out, and one can actually then, to a good approximation, state that the velocity at a certain radius inside the ejecta is just proportionate to the radius. And this is, of course, called homologous expansion or self-similar expansion. So that means that the relative structure of the ejecta in terms of mass distribution and chemical composition is then fixed in velocity space. Now, it's important to determine when this homologous expansion sets in. So we've actually tested this, and for at least general mass explosions, but this will actually not be very different for other explosion models. You could say, well, after 100 seconds or so after ignition, homologous expansion is reached to a good approximation. So then you have just this free streaming of the ejector, the ballistic expansion of the ejector, the homologous phase is reached. Of course, there is still one process that injects energy into the ejector, and this is the radioactive decays. And of course, this could still shuffle around material and accelerate material. So this has been tested by Stan Woosley and Sergei Blinnikov actually made calculations on this in this publication. But they actually claim that the effect is rather little. So you can have maybe a 10% change in the velocities of some parts of the material, but it's not a huge effect. So therefore, to a good approximation, you could say after 100 seconds or so, the ejecta are expanding in a homologous way. Now this has important implications for the modeling of the radiation transfer in supernova ejecta. So it may, and the first fact is that the ejecta will be optically thick to very long after reaching these 100 seconds, this homologous expansion phase. They will be optically thick for days or so. So therefore, at the time when you are interested in doing radiation transfer calculations to compute observable spectra or so, the ejecta will be in homologous expansion, and therefore it is actually safe to assume that radiation transfer and hydro have decoupled. So that means that in the end, you don't have to follow the formation of the observables by doing radiation hydro calculations, but you can actually just do the explosion simulation, follow it to homologous expansion. This sets the background structure on which radiation transfer takes place, and radiation transfer can actually be calculated in a separate step. Another thing that's something I will not talk much into detail here, that's the Sobolov approximation that holds. So this is an approximation that makes the treatment of the radiation transfer much more efficient, much easier. It has to do with the expansion of the material and the redshifting of the photons relative to the expanding material, and therefore you could actually, the idea is that the photons redshift through lines instantaneously in space. So this leads to an approximation that makes the calculations much easier. So in the end, these 2 points here that are just a consequence of the fast expansion of the ejecta make the modeling of the formation of the observables much, much more easy. But still, these are demanding calculations. So I already mentioned this the day before. Nowadays, performing hydrodynamic simulations of the explosion phase itself is still a task in 3D that you want to do on a supercomputer, but it's not really flagship computations there anymore. You need a few thousand cores, but not 100,000 cores for that. The radiation transfer modeling, if you do that in 3D, then this is actually rather expensive. In order to do that and to be able to do that in 3D, people rely on Monte Carlo techniques, and so that actually requires a minimum number of packages, Monte Carlo packages, to follow the random walk of the photons through the ejecta and to model the interaction. So all this is rather demanding, so you need a high number of Monte Carlo packages, and you want to take into account a high number of possible interactions with the materials, so millions of lines are included, and this makes these computations rather expensive. So these still take weeks on a supercomputer to compute. But it's possible to do them, and therefore it has been over the last maybe only 5 or to 10 years, maybe 5 years only, really become an industry to consistently connect multidimensional models to radiation transfer calculations. And the way this is done is that we have in our group set up a pipeline where we assume a progenitor structure. We talked about that there are uncertainties here, that we have to make an assumption of how the white dwarf that explodes looks like, how it ignites. Then we follow the explosion phase with multidimensional hydrodynamic simulation, and this then determines, of course, the hydrodynamic structure of the ejecta. Then, in a separate step, nuclear synthesis is post-processed or in a separate step then determined on the basis of tracer particles, and this then determines, of course, the chemical structure of the ejector, which is necessary for the radiation transfer calculations. And then multi-D radiative transfer calculations can be done on the basis of the hydrodynamical structure determined in the multi-D hydro simulations, like density profile, and the chemical structure determined in the post-processing step. This allows for radiative transfer calculations, and as mentioned before, this is usually carried out in multi-D for supernova explosions in Monte Carlo approaches. The questions that one wants to address with with radiation transfer is whether a particular model of a thermonuclear supernova explosion really matches observations of an individual type 1a supernova event. Another question is, do generic properties of a model translate to something that's characteristic feature in the predicted observable? So this would then allow to connect a particular modeling scenario with a certain observation, if it exists, with a certain subclass. You could say, well, in a certain model, we have actually a certain hydrodynamic effect. We'll see that, for instance, the mixing and turbulent deflagration is such an effect that directly translates to a specific form of a spectrum, and then you could say, well, this actually explains the spectra of a particular subclass of supernovae. And in the end, of course, the final goal is to explain with such models the range of diversity of observables, and in particular to reproduce the trends and correlations that are seen between these observables. The most famous and most important here is, of course, the visible luminosity radiation that is used to calibrate type 1a supernovae as distance indicators in cosmology. Now, a warning here, there's a uniqueness problem. So first of all, nature provides us with observables, and this is not actually something that we can choose, but this is what we get delivered, and it is not clear that this, in all cases, really tells us much about the actual explosion process. The early or around peak luminosity observables do not really test the inner parts of the ejector. This is just done in a nebula phase, perhaps. The information on the explosion physics may be hidden somewhere in the spectra or the light curve shapes. So this information may be limited or subtle. And in the end, it is possible, and we see that is actually the case, that quite physically different explosion models give rise to very similar predictions for observables. So in the end, one has to think of ways of breaking the degeneracy between models with respect to the predictions of observables. Okay, with this warning, we will just start reviewing different explosion processes and their predictions for observables. Let's start out with deflagrations and Chandrasekhar's white dwarfs. Synthetic light curves have been computed for various models. So here I actually show the predictions that have been derived by Stuart Sim and Markus Kromer from the set of deflagrations that were ignited in different ignition spark configurations that I showed in the last lecture, testing for different explosion strengths, testing out how bright supernovae ignited in this deflagration phase can become. And here are the spectra that are predicted from that. And you see that we have a range of the B-band light curves covered by our models. That's the colored light curves here. That is much fainter than the observations of normal type 1a supernova that are shown here in gray. So this is one thing that we actually immediately see. So these objects don't actually match normal type 1a supernova. They just don't become bright enough. The other thing that they don't match is the I-band light curve. The observed I-band light curve for normal type 1a supernovae has a double peaked shape, and this is not reproduced by these models. However, there is an interesting potential correspondence to these models in the observed sample, namely between the asymmetric ignitions that I discussed in the last lecture that leave behind a bound remnant because the deflagration then quickly moves to the surface, doesn't burn much material. The energy release is not sufficient to completely disrupt the star. So these asymmetric ignitions leave a bound remnant, but the predictions of observables for these events actually look very similar to what is observed for a certain subclass of supernovae, of type 1a supernovae, the so-called 2002 CX-like objects. So what one actually has seen for these class of Tapani supernovae that make up perhaps a few percent of the observed sample, 3% or so, is that they actually have a rather featureless spectrum around peak luminosity. So the silicon line is not very clearly seen here. So this is the characteristic feature of these O2CX-like objects, and they are also rather faint. So this featureless spectrum actually is reproduced by our turbulent deflagration models. And the reason for this featureless spectrum is that the rather mixed chemical ejecta structure due to these large-scale plumes and instabilities we have in a turbulent deflagration translates into a spectrum that doesn't show very clear spectral lines, spectral features. So this is actually a prediction from the model, from the mechanism, namely the turbulent combustion with all these instabilities, that this would lead to a featureless spectrum. And indeed, there is a subclass of Tapani supernovae, the O2CX-like objects, that have such a featureless spectrum. If you compare the light curves, then you find also a reasonable match, at least in some of the wave bands. So these are faint objects, as predicted by our models also. There's a bit of a disagreement in the later light curve phases, and it was discussed that this may be actually in the observations due to radiation that in the final phase then is due to the bound remnant that is behind. So you have a hard white dwarf as a bound remnant inside the ejecta. This was not taken into account by the radiation transfer calculation, so therefore we are missing here some of the energy input. So conclusion on the deflagrations in Chandrasekhar white dwarfs is that the sparsely ignited models are a promising candidate to explain O2CX-like objects. More vigorous ignitions, however, don't find any corresponding observation. So therefore, they could perhaps just not occur in nature, as suggested by pre-ignition convection studies, where people find it is more likely that an off-center single spark ignition happens. Or the alternative explanation would be that the more vigorous ignited deflagrations produce stronger turbulence and are therefore more likely to trigger a delayed detonation. So what about these delayed detonations in Chandrasekhar white dwarfs? Already quite a while ago, in 2009, we published a set of two-dimensional models where we varied the deflagration ignition geometry and also the conditions for our parameterized deflagration to detonation transition that was not modeled as sophisticatedly as it is nowadays. So we still had 3 parameters in this transition back then. And then Kaysen computed light curves and spectra for this sequence of models. And what we found was actually that there's a good match between predicted light curves and spectra and observations. So this was then systematically compared by Stéphane Blondin on the basis of a rather large sample, the CFA sample of well-observed Tapani supernovae. And he tested actually our models with an observer's tool, the supernova identification, the SNIT tool. This is actually used by the observers to classify supernova spectra. And actually this tool would decide that our model spectra are really Tapani supernovae, which is already a nice success. So the things that we model here as delayed detonations would be recognized by observers as Tapani supernovae. And also good matches of the models with individual observations can be selected by this tool from this large sample, and so one finds actually good correspondence between individual models and individual objects. However, there are some general problems. So in general, the predicted light curves by these delayed detonations in Chandrasekhar white dwarfs are too red, and the spectral features show systematically too high ejecta velocities. A nice feature of this set of models was that it actually seemed to follow, at least in a certain sense, the trend of the width luminosity relation. That's the observed width luminosity relation. Here we have the peak luminosity, and here the B-band decline rate in 15 days. So that's the Phillips relation of width luminosity relation. The gray band is the observed width luminosity relation. This is what our models predict, and you see we have a much wider spread, but in principle there's a trend in this direction. And also the correlation between the peak luminosity and the color that's also used for calibrating Tapani supernovae as distance indicator is in a sense followed by a model. So this is a nice success. However, well, you'd say, well, problem solved. But then we tried 3D models. And 3D models did not actually show the same result. Although, in principle, they don't look really bad. So this is actually something that was analyzed by Stuart Sim. He performed radiative transfer calculations based on this model sequence with different deflagration ignitions that were later then turned to a detonation. So again, a sequence of models with different models, 3D models with different deflagration strengths, then giving rise to variations in the nickel-56 production and in the energy release in the delayed detonations. So again, Stewart computed synthetic light curves and spectra, and he also did a systematic comparison based on the SNIT tool and found relatively good matches of our predicted observables with individual spectra of supernovae. So examples are shown here on the right-hand side. But there are still problems in detail, and these are essentially the same that Stéphane Blondin also found. The line velocities are too high and the colors are too red. The light curves actually predicted from these 3D explosion simulations also show a rather wide spread, but they fall into the range of what one would expect for normal type 1a supernovae. The problem, however, is that what Stewart found was that the width luminosity duration is not reproduced. So again, here is the peak luminosity in B band. Here's the decline rate in the B band. These green data points mark the observed width luminosity duration, and these gray data points, the black data points are angle averaged the correlation measured from angle averaged light curves for different models. You have the spread here with viewing angle effects in gray, but you see what that we get actually from these 3D models a relation that's almost perpendicular to the observed one. Well, what you could also say is, well, we see quite a bit of variation in the peak luminosity. We have different nickel-56 masses in the models, but we don't see much of a variation of the decline rate in the B band. Well, this is a bit puzzling. We are not quite sure why that is, why 3D is so different from 2D. So the suspicion is that in these 3D models, we actually used a more sophisticated way of describing deflagration to detonation transitions based on turbulence effects with the subgrid scale model, and this fixed this parameter, whereas we still kept it as a free parameter more or less in the 2D version of the model. And if you actually look closely into what produces this trend in this direction, it seemed more that this was really the deflagration to detonation transition conditions. Okay, but you could still say, well, now we have fixed the deflagration to detonation transitions to something that we think is more physical. And this then actually then the ignition geometry does not deliver a trend in the direction of the width luminosity relation. So therefore it could be another parameter of the exploding white dwarfs that sets this trend, the width of the width luminosity relation. So therefore we looked into other parameters. And one, of course, physical parameter of the exploding white dwarf is its chemical structure. It's carbon to oxygen ratio at the explosion. And this is something a student of mine looked into, Sebastian Ullmann, and again, Stuart Zimmer, Markus Kromer computed synthetic light curves and spectra from these simulations, and you get, again, a trend that is perpendicular to the width luminosity relation. So at the moment, it's not clear whether you can, in 3D simulations, produce such a width luminosity relation. One has to keep in mind, however, and this is what the radiation transfer people stress, that determining this delta M15, the decline of the light curve in the B band 15 days after peak luminosity, is a quantity that's very hard to predict reliably from radiative transfer calculations, because this actually is afflicted with uncertainties in the NLTE structure and the ionization structure, NLTE conditions and the ionization structure of the ejector. So this is a very uncertain quantity to predict from radiation transfer modeling. The observers, however, like it because it's an easy to measure quantity. So the width luminosity relation is not followed either by the ignition geometry nor by the carbon oxygen ratio. So these do not seem to be the parameters that drive these relations. So therefore, the verdict on, well, I should also say we also tested the gravitationally confined detonation model that was originally suggested by the Chicago group. And as expected, the observables don't look like anything that we see for supernovae because of the ejector, of the deflagration that is at the surface of these ejector structure. So this actually makes the observables not compare well to observations. So therefore, final verdict on the Chandrasekhar Mars explosions. Asymmetric deflagrations in Chandrasekhar Mars white dwarfs seem to reproduce O2CX-like objects well. The late detonations look in principle promising for reproducing characteristics of individual objects, so this is actually nice, but they have problems with following the trends. This could be, as I mentioned before, a problem of the radiative transfer modeling, or it could be a generic problem of the entire scenario. This is hard to disentangle. I will just give you speculation on what it means if this is really a problem of the physical scenario. Well, it could actually lead to this speculative interpretation that in Chandrasekhar mass white dwarfs we have only deflagrations and no delayed detonations. Delayed detonations just don't work. And the ignition is, according to also what is found in pre-ignition convection simulations, just asymmetric and in a single spark or connected region of center, and multi-spark ignitions don't exist. So this would actually lead to the interpretation that then all what Chandrasekhar mass white dwarfs do is asymmetric deflagrations leading to objects that look like these O2CX like Tapani supernovae, but normal Tapani supernovae would not be produced by this. Another argument in this direction is that population synthesis in most cases predicts that it is rather hard to form Chandrasekhar mass white dwarfs, and they could at best make up a few percent of the observed sample of Tapani supernovae. This would actually go well in line with the interpretation that only O2CX like objects are made by them. But this picture is just speculative. This is not finally settled by current simulations. We have to still work on uncertainties in radiative transfer. More work is required before one can really finally decide on this. But it motivates looking into other scenarios, and this is actually part of the reason why we looked into sub-Chandrasekhar mass detonations. So the first thing one can do there is to test the overall capability of sub-Chandrasekhar mass white dwarfs to produce something that looks like a Tapani supernova. And this was done by artificial detonations in sub-Chandrasekhar mass white dwarfs of different masses. So Stuart Sim actually, so this is actually sub-Chandrasekhar mass white dwarfs of different masses where we artificially ignited a detonation in the center without giving any physical reason for why this should happen, to just see what these objects would look like. And so Stuart Sim actually then computed synthetic light curves and spectra from these objects, and they look promising. So you get actually light curves and spectra that compare rather well to observed normal Tapani supernovae. So light curves and spectra, so here gray spectra observations, and you see the spectra that are predicted by the explosion models with varying masses of the exploding sub-Chandrasekhar mass white dwarf. Now the interesting thing is that these models actually give rise to a trend of the connection between the peak luminosity in delta M15, the decline rate of the light curve that follows the observed, with luminosity relation. At least the trend is correct. So this is again data points in gray, models are shown here in black, and you get a trend in this direction. So you vary the peak luminosity and the delta M15, the decline rate of the light curve. So here, the luminosity trend is followed, and it's connected to a very clear physical parameter that drives the relation, namely just the mass of the exploding object. And this was already suggested as the primary parameter, giving rise to the width luminosity relation by Pinto and Eastman in 2000. So this, in principle, looks promising, but these were toy models, artificially ignited at the center. We didn't give any physical reason why they should undergo a detonation. We talked yesterday about potential scenarios that could give rise to a detonation in a sub-Chandrasekhar mass white dwarf, and one was the double detonations. So this was when the white dwarf accreted helium from a companion star, and if the helium layer is massive enough, it will undergo a detonation, drive a shock wave into the carbon-oxygen core, set off a secondary detonation there, and this gives rise to the supernova event. Now if you model spectra of such explosions, as Markus Kromer did from our double detonation scenarios, you will see that these models have a substantial problem. And the problem is because you have first the detonation in the helium layer and only later the detonation in the carbon-oxygen core. So that means that the outer part of the ejecta will be dominated by the products of the helium explosion. And helium, again, produces very easily heavy species. So we have quite a bit of elements like chromium and titanium in the outer parts of the ejecta. And what they do is actually they shift by fluorescence the flux into the red. And this is clearly seen here. So in blue, there's an observational spectrum shown, and our model prediction is the black spectrum here. And this, as you see, has way too much flux in the red. Color-coded is actually the species that gave rise to an absorption and an emission. So absorption is on top and emission on the bottom to the last photon that was followed with the Monte Carlo radiation transfer approach. And this actually indicates that it's really this chromium and titanium that give rise to this redshift of the flux that is not consistent with the observables. So these double detonations therefore have a problem. The heavy species synthesized in the helium shell detonation shift the flux towards red colors way too much. But one has to caution here again, because this is preliminary. The results from the radiation transfer depend strongly on the calculation of the plasma state. And there are great uncertainties here with the treatment of the non-local thermal equilibrium, and also the atomic cross-sections are not all known. So we have incomplete atomic data here only. So therefore, this is what we actually arrive at as a conclusion at the moment, but this may still change with improvements to the radiation transfer calculations. Okay, one side remark, because I actually named this lecture course Thermonuclear Supernova Explosions. I did not say type 1As. In principle, it's possible that such scenarios also give rise to other transients that are not classified as type 1A supernovae. These faint and fast transients that have been observed with larger surveys over the last 5 years or so. And actually, if you do these double detonation calculations with lighter subchannel second mass white dwarfs as the core, so not around 1 solar mass, but going down to 0.8 solar masses, that they actually don't produce much nickel-56 and become very faint, then they actually are good candidates to compare them with these faint and fast transients. And there has been a particular observation that has been attributed to one of these double detonations. Finally, violent mergers. The merger scenario in the variant that is calculated by Röpke, where the ignition of the primary as a subchannel second mass white dwarf happens in the inspired merger phase. This actually produces observables, light curves, and spectra that compare very well to normal type 1A supernovae, as expected from an explosion of a subchannel second mass white dwarf. So this is not a big surprise. Here you have an explosion of a subchannel second mass white dwarf that is almost undistorted by any layer of ejecta above it. So therefore you get actually what you would expect for a subchannel second mass white dwarf, and this fits the observations really well. So therefore the verdict of the subchannel second mass explosions, this could work well in principle. Double detonations have the problem with the helium shell detonation ashes, but this actually needs to be settled with improved radiation transfer treatment. The violent mergers look promising. I cannot present any prediction for the width luminosity relation for the violent mergers yet, because these are rather expensive calculations and we don't have many for them at the moment. So Rüdiger is only part-time working on this. He is now most of his time a cosmologist and works only on type 1A supernovae as a hobby. So we don't have so many predictions for this yet. So the one or two calculations we have look promising, but more detailed exploration of the parameter space is necessary. So I've shown actually most of the observables that were derived from our group. So this is because not many groups actually achieved to set up a full modeling pipeline to really connect the explosion simulations to observables, but there are other groups who actually are able to do similar things. And one example you find in literature is actually the head-on collisions that were calculated by Stefan Rosburg, and for these then Kaysen computed synthetic observables. He looked into light curves, spectra, and the width luminosity relation. Here you see the results. And the conclusion is, at least if you have a head-on collision of two rather massive white dwarfs of 0.9 solar masses, then they could produce something that looks similar to a normal type 1A supernova. The problem, however, is, I showed you the typical ejecta structure yesterday. The ejecta, the composition of the ejecta is rather asymmetric, and therefore you have huge viewing angle effects. And this is actually something that is not really expected for normal type 1A supernova. Okay. So finally, what do we actually learn from all this? Well, we can in the end, try to distinguish different explosion mechanisms by their predicted observables if we compare them to actual astronomical data. So let's try this on the basis of supernova 2011 FE. This was a very close supernova, very well observed, with different explosion mechanisms. So on the left-hand side here, I have the predictions in black from a Chandrasekhar mass delayed detonation. On the right-hand side, this is a merger model. And you see that both models actually sort of catch the right spectral features, but there are discrepancies in detail for both of these models. So it's very hard to say whether the merger or the delayed detonation is better. And this is quite surprising because the physical mechanism is very different. Where one involves more than a Chandrasekhar mass, the other involves a Chandrasekhar mass in the explosion. The one actually involves only a detonation, the other has a deflagration phase. You would expect to see quite a bit of differences, but actually this is, at least as the level as our radiation transfer is predictive, not really so clear. So therefore, one wants to break the degeneracy between models with alternative observables and constraints. And I've actually just made a list of this here, so this would require a discussion that would easily take another 2 lectures. So I will just give you a list of what has been attempted there. So one possibility is late light curves. This is sensitive to nucleosynthesis details and quite promising, but hard to measure because you would need to have the bolometric luminosity, the bolometric light curve at 1,000 days after explosion. And this is very hard to get because it's not clear that all the flux is in the optical, which is already hard to get. You may actually have flux in the infrared, which is impossible to get for these faint objects. So this is afflicted with uncertainties. But in principle, theoretically, it's a promising way of distinguishing between models. The Nebula Spectra, as said before, test directly the inner part of the ejecta, and this is promising. Cecilia Cosma computed Nebula Spectra of one of our deflagration models, and this deflagration, of course, as I told you before, leaves behind this downdraft of unburned material near the center, and this was found to create a problem in the Nebula Spectra. You see a strong oxygen line in the predicted Nebula Spectra that is not seen in the observations. So in this way, you can, in principle, test the inner parts of the ejecta. The prediction of Nebula Spectra, however, is still a rather complicated business. People are working on this at the moment in Belfast, in Stewart Simms Group, for instance, and we are hoping to be able to compute Nebula Spectra in a more standard way in our pipeline, but this is not the case at the moment. Polarization is also something that has been looked at because it directly tests symmetries and the multi-D structure of the ejecta. This is again promising. And here, Stewart Simms Group has been able to generalize their radiation transfer code to also make predictions for polarization. And this was published by Mattia Buller just last year, where he actually compared the predicted polarization signal from a violent merger, a Chandrasekhar mass, delayed detonation, and a sub-Chandrasekhar mass double detonation scenario. So he took our models as input data, predicted polarization signals, and found that there are differences. The variant of the merger scenario that he actually took is rather asymmetric, and therefore would actually fit only the highly polarized observed supernovae, well, at least highly as much as it gets for Tapani supernovae, which overall have a rather low polarization. And the other 2 models actually agree very well with the low polarization that is seen for normal Tapani supernovae. High energy observables can also be predicted. Of course, in the radiation transfer, we do, of course, gamma ray spectra and light curves are automatically predicted. In X-ray, you can also make some argument of specific X-ray lines that could actually be observed for specific models. So this is another way to distinguish between the models. The problem here is that the current instruments that we have are not sensitive enough. I mean, we have a detection of gamma rays of supernova 2014J, but just a detection. But this actually does not measure any light curve or spectrum. So prospects for this don't look so bright from the observational side. So we can make predictions from the models, but the observations are hard to get. Then there are constraints from the nucleosynthesis. If we have burning in the channel Sekar mass white dwarf, then of course the densities are rather high, and this leads to rather high neutronization of the ejecta. So this is a clear prediction that the channel Sekar mass models make. Whereas in the subchannel Sekar mass explosion, the central densities are not so high. We don't have strong electron captures, and therefore the material is not so neutronized. Then we have differences in the freeze-out from NSE, alpha rich or normal freeze-out, and this actually makes specific predictions for the yields. And I want to at least give you this example in the last minutes. The constraints on nuclear synthesis from different explosion models that directly translates to predictions for the light curves, late light curves that are actually sensitive to nuclear synthesis effects. So the idea here is the following. Let's take a look into the density temperature plane of material when it reaches burning. So that's the peak temperature versus the peak density of a fluid element that's reached in the explosion. So that's what it actually burns to. And here we have all the traces in this parameter space for different models. So we have here a double detonation model. We have here a violent merger. This here is a pure deflagration, turbulent deflagration of a channel Sekar mass white dwarf. And this here is a delayed detonation of a channel Sekar mass white dwarf. The green lines here actually are put in according to Woosley, specifying the region where you have incomplete burning. This is this left part of the diagram. Normal freeze out from NSE is here in the upper right corner, and in the lower right corner we have alpha rich freeze out from NSE. And what you see here is the nickel 56 and iron group production is taking place at very different places in these models. So in the double detonation we have predominantly this taking place in incomplete burning, and in average freeze out, because the densities are low, we have high entropy NSE, and some of the iron group elements are produced also in the helium shell detonation. The mergers actually, because they're also subchannel Sekar mass models, also produce iron group elements predominantly in the average freeze out. Whereas the channel Sekar mass models produce substantial amounts of nickel 56 in the normal freeze out from NSE. That's just because they burn at high densities and we have low entropy NSE freeze out here. Well then, you can look into what is predicted for a specific isotope, namely cobalt 55. Cobalt 55 is produced only in alpha rich freeze out or incomplete burning. And the reason is that cobalt 55 gets destroyed in alpha rich freeze out by proton capture. So it just produces then cobalt 56, and so you destroy this in alpha rich freeze out. So therefore only the models that actually have substantial normal freeze out from NSE, so that is the channel Sekar mass models, produce appreciable amounts of cobalt 55. Now why is this interesting? Well, this is interesting because cobalt 55 decays to manganese 55. The manganese is a good element to observe because manganese in nature occurs only in this one isotope as manganese 55. Now this has been studied in stellar abundances where we of course are not sensitive to isotopes but only to elements, but this is actually manganese can be studied because it's a single isotope species. And there are measurements for how the manganese ratio evolves in galactic chemical evolution. So it is low at early times, and this is thought to be the contribution to manganese production by core collapse supernovae. And then it goes up to reach the solar value, and this bending upwards in the data is interpreted as the Tapani supernovae setting in. So the only place, the only astrophysical site we know actually where we have alpha rich, not alpha rich but normal freeze out from NSE so that manganese can be produced in substantial ratios with respect to the iron is in Chandra Sekar mass white dwarf explosions. So this is just to give you an argument after I actually told you why Chandra Sekar mass explosions from the predicted observables like in spectra don't look so promising. Here's an argument why you still need them in order to produce the manganese. And even if you don't believe the predictions of galactic chemical evolution, you could just take the solar value here. And this is very solidly measured in meteoritic abundances, so we exactly know what the ratio of manganese to iron is in the solar system. So you have to reach that, so you need at least a few events that produce this ratio in the solar values. and this is only in Chandrasekhar mass explosions. And therefore, if you want to fit this trend here, you need something like a substantial contribution to the overall production of manganese by Chandrasekhar mass explosion models, maybe 50% or so. That's the prediction here. Now, another prediction this makes is for the late light curves. So in the beginning, up to 1,000 days or so after explosion, the light curve is driven by the nickel 56, cobalt 56, iron 56 decay. But then the ejecta have become dilute and are not optically thick to gamma rays anymore, and also the nickel 56 and cobalt 56 has decayed to a large part. And this is then the point after 1,000 days where the decay of other isotopes in the leptonic decays take over and dominate the light curve. And this makes the light curve bend over, so its decline will be shallower then, because then the other decays become important. And at some point, like 1,400 or 1,800 days after the explosion, an important contribution will be due to the decay of iron 55, cobalt 55, manganese 55. And this is predicted again to be different in these explosion models, whether or not you have a Chandrasekhar mass exploding there or not. So therefore, just taking two measurements at the late light curves of the bolometric late light curve, say at 900 days after explosion when you still are dominated by the nickel decay, and 1900 days after explosion when you are dominated by this iron 55, cobalt 55, manganese 55 decay chain, just taking this ratio should tell the models apart. The problem is getting data points for these late light curves, 1800 days after explosion. That's nearly impossible. What else do we have to break the degeneracy? Well, there are non-electromagnetic observables. We could predict the neutrino signal or the gravitational wave signal from different explosion channels. This has been done by a number of authors for different explosion scenarios, and they make actually predictions that they should have distinct features in neutrinos and in gravitational waves. However, the neutrino signal and the gravitational wave signal of type 1a supernovae of all kinds is expected to be very weak, so there are little prospects to actually observe that. Ejecta masses, well, this is another way to distinguish between Chandrasekhar mass explosions and sub-Chandrasekhar mass explosions naturally. The question is, what do observations tell you about the ejecta masses? And this was actually then tested by Max Stritzinger and Jit Scalzo, who actually on the basis of large sets of observations tried to predict what the ejecta structure in these type 1a supernovae, in the observed type 1a supernova would have been. This is afflicted with large uncertainties, but it seems that they find that the significant fraction of these objects don't reach the Chandrasekhar mass in the ejecta and are sub-Chandrasekhar mass explosions. Rates and delay times, well, this sets constraints on the progenitor evolution scenario, but is afflicted with large uncertainties, as we already discussed. But this has been discussed in the literature quite extensively. Final remnants of type 1a supernovae, in principle, you could hope from the chemical structure of the remnants as studied in X-ray observations to learn more about the ejecta structure, but these measurements are complicated and hard to interpret because the ejecta, the remnant, in the remnant phase, the ejecta interact with circumstellar material quite substantially, so it's hard to interpret this data. Another possibility would be to look into the remnants closely and see whether you could identify a companion star that you would expect in the single degenerate scenario. Single degenerate scenario was a white dwarf accreting material from a companion star, from a normal star, to grow in mass to the Chandrasekhar mass and then exploding. Then, of course, it would hit the companion star with its supernova blast wave, but the prediction is that the companion star survives this and is still there. So people have looked into this. Pilar Ruiz La Puente claimed that she had found the remnant of the companion star in the remnant of Tycho Brahe's supernova. This was disputed by Wolfgang Kerzendorf, so it's not so clear. And Brett Schaefer and collaborators have looked into remnants of type 1a supernova in the LMC. And here you have a rather clean field. There's not much stars in there. And in the center, where you would expect the companion star, if the single degenerate had given rise to the explosion, there's no star detected at all. So they can make actually, to their observational limits, they can actually exclude quite a number of possible progenitors. So this is where I want to conclude. I just want to show you how we know that the progenitor survives. So this has been simulated. Here is such a simulation. We have the companion star and the supernova going off. Supernova blast wave hits the companion star, and this can be actually simulated with SPH simulations. This was done, so it would predict two things, or three things. It would predict the velocity of the companion star. It would predict whether or not you can actually deposit some of the explosion burning products on the companion star. And as you see, quite a bit of the outer envelope of the companion star is expelled by this interaction with the supernova blast wave. Although the companion star overall survives, quite substantial material is expelled off from the companion star. And this, of course, is hydrogen helium material, which you should not see in Type 1a supernovae. So again, you can actually then play the game of putting limits on how much such material from the interaction with the companion star you can still tolerate to produce spectra that don't show any traces of hydrogen and helium. Okay, so this is the last thing I wanted to show. In this course, we covered quite a bit of material, starting out from some general ideas of white dwarfs and reactive fluid dynamics that can give rise to explosions, thermodynamic explosions due to thermonuclear burning processes in these white dwarfs. So this is what we then also discussed. I gave you at least some sense of what we do for simulation, for the simulation of these objects. We talked a little bit about progenitors and the ignition, possible ignition scenarios for thermonuclear supernovae. I've given an overview of different multidimensional explosion simulations, and now we discussed the observables. So this hopefully was able to give you a good overview of the field of Type 1a supernova research from the theoretical side. All right, so that's it. Thank you very much for your attention.
Thanks a lot, Fritz. Any questions? It's your last opportunity.
So you mentioned a lot of different observational ways how we can shed light on the model and progenitors, but you personally, which one of them?
Yeah, well, I mean, this is the list that we try to push, right? So,
seems more promising, and as a theoretician, which kind of survey probably you're waiting for?
No, what I'm waiting for is actually that our collaborators in Belfast will hopefully provide us with predictions of the Nebula Spectra of our models. So that would be very, very useful. So that's the next steps. Polarization has been done, and it actually gives results. And now the idea is that we have to set up the pipeline, so we will sort of in a standard way always also produce polarization prediction of our models, and this then can be compared to the observation. Of course, there's not so many spectral polarimetry observations of Type 1a supernovae. There's maybe, I don't know, 15 objects or something like that. So these are very expensive observations, but there is information there that can be used. And for the Nebula Phase, that's perhaps a little bit easier to get from the observational side, and this would also make good predictions. And we are hoping that this actually will also help to break the giants between the models. Because one thing is, you look into the center of the ejecta, right? And in substandard mass white dwarfs, you would not expect to have any stable iron there because everything burns to nickel 56. You don't have neutronization there. And in other models, you do have that there. And the question is whether you would see it or not, whether you would see traces of the unburned companion in double degenerate mergers, in the violent mergers scenario in the center of the ejecta. So these things can be tested in principle.
You mentioned head-on collisions of white dwarfs. It is intriguing because such an event is exceedingly rare, I guess, from the point of view of dynamics. So is it expected to occur frequently enough to be considered?
No. Well, I mean, the thing is that Stefan Roswog made this prediction just because he had the tools for it, and he then argued that maybe in globular clusters you could actually find this, and he predicted this would be a very, very rare event. But then there was a group in Princeton, Boskatz and others, they pushed very hard for the idea that with the Kozai instability in triple system, you could perhaps go to a more frequent occurrence of these head-on collisions, or at least collisions of white dwarfs, maybe not head-on, but grazing collisions. But I don't know how solid all this is. They actually run around at conferences and make strong claims, but it's not so clear whether this is actually a working scenario. I would also be skeptical.
Another question? Yes?
So I just have a comment that gamma rays, you are being pessimistic because they're hard to observe, but there's a lot of missions now being proposed in NASA that are going to really, make it so we can see almost 10 times further out.
Yes.
And that will increase the number of gamma rays detected in 1As by a large amount. So it could be in 10, 20 years.
Yeah, exactly. So that's. I mean, I'm being a bit pessimistic talking to Roland Diel too often, and he always would tell his students, well, in your lifetime there will be no new mission.
So I know for these 2 NASA missions being proposed that will be...
It would be helpful, yeah. I mean, the prediction is now that you actually would need at least a galactic supernova to see anything. Yeah.
Yeah. What was about the light curve you showed? The red ones at the secondary peak.
Oh yeah, right. Yeah, I'm not a radiation transfer modeler. I think this has to do with the change of the thermodynamic condition in the ejecta that give rise to a change in the ionization of iron. And so I think the Enkeson's explanation for the decline of the B-band light curve is that by change of this ionization, flux is at some point shifted, I think iron 3 to iron 2 or something like that, that flux is shifted from the B-band to the red band. And you get the second peak there, and this actually also is connected to the decline rate in the B-band. But it's a complicated to model effect because of the ionization structure there.
Yes, I have a provocative question. Imagine you give this, you have given this lecture in front of the Nobel Committee. Do you think they will have attributed the prize?
for supernova cosmology?
Yeah.
Well, I mean, supernova cosmology, of course, in this perspective is just an observational thing, right? I mean, what they actually could show is, for instance, if they take the observational Hubble diagram and employ their calibration techniques, the scatter gets smaller, right? And of course, I mean, you could say, well, people would not have believed this too much if there was not for alternative tests of cosmology. And I mean, you have baryon acoustic oscillations, and you have CMB, and all these, either 2 of these predict the same thing, right? So this actually helps. And they were the first to claim it. But of course, I mean, the thing is, the nice thing is with Tapani supernovae, it's not so much appreciated by the cosmologists because they also think it's too dirty astrophysics, too many effects in there, and CMB is much cleaner, right? So this is actually, but the nice thing is that Tapani supernovae really test for the geometry directly, right? So really measure distances, so it's not that indirect. And actually, it's in many cases sort of the predictions are perpendicular to the other things, so that helps to break the degeneracy between other measurements.
In the single degenerate scenario, you have the companion, which is which undergoes this blast, and one could expect that it is enriched by the iron that is produced by the supernova.
Right.
So would it be realistic to imagine a survey for iron-rich stars that would be only explainable through this kind of history?
Well, I mean, the thing is that what you saw there is you actually expel much material, so it's hard to really deposit a lot of material. But actually, the deposits are not so bad because you have the iron in the inner part of the ejecta blast space, so this will hit the companion star last with low velocity. So there is a chance to deposit some of the material. So we tried hard by increasing the number of SPH particles in these simulations to make a prediction for that. And this is especially because Pilar with La Puente, for her companion star that she claims is the single degenerate companion star in Tycho remnant, she actually claimed to have measured an increased nickel abundance. But this was again then disputed by Wolfgang Ketzendorf, so it's not so clear whether this is a solid measurement or not. But there was a claim that there are chemical anomalies in this Tycho G star, which is supposed to be the single degenerate companion, and therefore we have looked into that. Actually, this can also be done for Kokolab supernovae. So we have actually also done this because there are these hypervelocity runaway stars that maybe are from Kokolab supernova explosions, binary systems, and there's also predictions that they could be enriched with. Yeah. And so my student who did these simulations also ran such a simulation.
Well, if not, let's thank